So, very good evening, friends. This is another session we are going to start related to multimedia. So, in this session, we are moving forward with another couple of algorithms related to data compression. So, do you have any questions related to our last algorithm? And I gave you some task like one was related to Hoffman coding. So you have to uh, make Hoffman code for your name or some other family members or any friend's name. So anyone have any solution or they provide, then they can write in chat. Otherwise, I'm going to start the session. This is session 5 for our subject multimedia, and in which we are going to discuss various other data compression codings. So other than the attendance, no one write anything. These are the guidelines for today's session. And so by the end of the session, you will understand more about the arithmetic coding with higher order modeling, finite context modeling, dictionary based compression, sliding window compression, and adaptive Hoffman coding we will also discuss. It's not written here, but we will discuss. So last time we discussed two techniques. One was related to Hoffman and another was related to Shannon-Fanon. So what was the Shannon-Fanon? What was the Hoffman? I'm giving you a quick recap. What was there? So we discussed Hoffman coding, in which we were like, just a second. So in that Hoffman coding, we were doing uh, like according to the frequency of the symbol or character, we were making the code or compression code by which we were showing that this particular character is how many times it is repeated. So what was the first step? First step was that uh, by any given uh, input or a string, we were finalizing first step as a frequency. So we were calculating the frequency. Frequency means how many times a character is repeated. Like in the example showing here, we have A, B, C, D, E, F, and we have a frequency like 5, 9, 12, 13, 16, 45. And we were starting with the first string that like A was the first character. We were starting with A, then B is like greater than A, so it was on the right side, and we were making the total of A and B. Thereafter, we had another sequence like C and D, so we were writing like C and D, and the total of the C and D is on the upper side. And thereafter, with each character, we were finalizing, we were adding the character. Thereafter, we were checking that is switching or swapping is required. Like if left hand side is greater than the right hand side, then we have to make it in ascending order. So each time we were adding the character, and we were like checking that is it in the same sequence that we required in ascending order. If it is not in ascending order, then we were swapping the nodes. So at the end, finally, we were finding the total of the all the frequencies. Like here we have 100. It means that 100 is how 100 is calculating. if we are adding all the frequencies from A to F, then the total will be 100. So if you have any confusion, like there is a mistake in that particular totaling, then you can easily check with the addition of these frequencies. If the addition is matching with this, then you can also write the code. One easy picking related to those characters in Hoffman coding was that if a particular character has higher frequency means it is repeated many times, or most of the times, then it has the lower byte code, or we can say that the lower compression code. Like here, F has the highest frequency, show 45. So F has the least code in term of symbols. Like F has the code only 0. In term of frequency, E has frequency 16. So E has the code 111. So which is another, like C has frequency 12. So C has code like 100. So we can easily check if uh, a particular symbol is repeated so many times. So it has the higher frequency other than the other. So this was the Huffman coding, and we had another term that was the Shannon-Fano coding. In Shannon-Fano coding, the starting of the like compression was similar to this. Like we have A, B, C, D, E, and we have all the frequencies like 15, 7, 6, 6, 5. Then we were doing the we were finding the mid range. So if we are calculating the approximate mid range, then thereafter we were allocating upper to the mid range is to 0 and lower to the mid range is to 1. And each and every time we were doing the same operation again and again. Uh, Whatever the sequence it is, we were checking that what is the approximate midpoint. So we from the midpoint we were grouping it into two parts, upper part and lower part and upper part. Lower part was assigned as zeros. Here we show that 0 is the code for upper and 1 is the code for the lower digits. So in the same way we were repeating, and we were uh, calculating each and every time by checking the midpoint. So the code is generated like at the end we have 0 0 0 1 1 1 1 1 0 1 1 1. So if we check, A has the least code like A B C and D E. So if A B C has code in 2 digits and D and E has code in 3 digits, so we can easily check that A B C has higher frequency than D and E. So here we have A B C. So A B C means A B C has the higher frequency as compared to D and E. So D and E has frequency 6 and 5. I hope there were no issues related to these two. Then we are moving forward with adaptive Hoffman coding. I'm checking if anyone has done, like Divya Jyoti is has done the name. So might be that was related to Hoffman code. So at the end we will check that is was it a correct code or not, or uh, one by one I will take another 5-10 minutes at the end, and I check and uh, provide you the answer. When another student gave me the Hoffman code for her name. So that's good. You did some task related to homework. So we are starting another session, like another topic in this session that is related to adaptive Hoffman coding. So adaptive Hoffman coding is somewhat similar to Hoffman coding, but there are some changes made in Hoffman coding to improve the algorithm. So adaptive Hoffman coding is a method used in data compression to encode data more efficiently. Unlike traditional Hoffman coding, where the frequency of symbols in the data needs to be shown in advance, adaptive Hoffman coding dynamically adjusting the code book as it encounter new symbols. So we do not have frequency at the beginning of the algorithm, but whenever the character or the string is adding, then dynamically we are adjusting. So overview of like Hoffman coding, how it is working. So we are starting from the initially the code like code book is empty. So as the symbols are encountered in the input data stream, they are encoded using the current code book. So when a new symbol is encountered for the first time, it is added to the code book with a code that doesn't conflict with existing codes. So I will refer you with example in our upcoming slide. So this is the basic that we have to do. So each time when a symbol are added to the code book, the tree structure is representing the code book is adjusted, maintaining the Hoffman property. What was the Hoffman property? The Hoffman property was saying that each and every time whenever a pass is completed, we are checking all the nodes are in ascending order or not. If that are not in ascending order, so we are swapping the nodes higher on the right side and lower on the left side. So on each pass, we have to do that. And here we have the much needed thing. Here we have is the symbol NYT. NYT is not yet transmitted symbol to indicate a new leaf is needed in the tree. So whenever a new leaf is inserted, new leaf means a particular character or symbol that is not encountered so far. Like if we have a particular, I will give an example. So you will easily understand what is the meaning of that particular thing. So how, on what principle Hoffman coding is working? It is working on adaptive Hoffman principle. In an optimal tree for n symbols, there is a numbering of the nodes, like numbering of the nodes, like y1 is less than y2 less than y2 and minus 1. So such that there are corresponding weights, like weight is x1, x2, x3, x. So we are saying that siblings are numbered consequently and vice versa. So if there is such a numbering, then the tree is optimal. We call that node number invariance. So we are taking with an example. Here is the example. We have a code uh, that we need to do adaptive Hoffman coding for AAR, D, VARK. So each and every time, whenever we do a new symbol or new character, so we are introducing NYT. NYT means it is a not yet transmitted that particular symbol. So NYT is always on the left side and its weight is always 0. You have to understand what I'm saying. NYT is whenever NYT is required when a new symbol, like here we are starting. So if we are starting, there is no symbol yet transmitted. So if no symbol is transmitted, we are starting with NYT. So NYT has a weight always 0. I think this is the basic step which you have to you have to memorize it. Like whenever we are introducing a new step or a new character, then NYT is used, and value of NYT is always 0. Fine. So if that particular character is already in the tree. So we are not going to use NYT. We are just updating. I will show you how we'll do that. So this NYT is the external node. And every time whenever we are adding a character, which is always a external node. Which one is the internal node? Those who are showing the total of left and right is the internal node. If any node is at the leaf node, so leaf node are represented as external node, and branch node, or we can say that the root node is used as the internal node. So I'm giving you one by one. First step is like we have first symbol A. So for A, we are using NYT on the left side, as A is used for the first time. If A is used for the first time, we are placing NYT on the left node, and on the right node, we are showing A. One is showing A is used at for one time. This is A. Then we are adding 0 and 1 left and right, and we are showing the total of left and right is 1. I think step 1 has no issue. Then we are moving for the second character, that is also A. So A is not a new character now, because we already did same thing for A. So A is not the new transmitted digit. It is already existing disease digit. So we do not need to encounter NYT again. So NYT is already present, and we are adding this A to this particular node. So A had initially the weight 1. Now A has the weight 2, as we have a new A in the tree. So now weight is increased. Now A has a weight 2. And if we are checking the Hoffman is satisfied, as this node has weight 0 and this node has weight 2. There is no issue. So we are updating the calculation that now the new weight of root node is 2, which is the total of 0 and 2. Any doubt? If anyone has any doubt without my asking, you can raise your question, then I can stop, then answer your question. So in the third step, we have R. So this is for R. R means, is R introduced for the first time, or it is a repeating? It is introduced for the first time. So if a character is introduced for the first time, then it means that we are going to use NYT. So here we are using on the left side, we are updating this NYT. We are updating this NYT. We are shifting this NYT to the lower with on the left side, and we are introducing the R. This R has weight 1, as it has the symbol repeating on the one time. So we have R weight 1, and we are adding these two with a weight 1. After the step completion, if we check, is this satisfying Hoffman coding, like left and right combination? Is it correct or not? I'm not going to uh, talk to you. I'm just asking the question. Is it correct by Hoffman coding? I have a couple of questions. Increase A quantity at second time from 1 to 2. Yes. Why? Because we have another character that was also A. Initially, A has a weight 1. Now A has weight increased because we want to use another A. If we have another A in here in this, so we will be adding this A to the same place where A is added. At the end, I will show you. So now tell me, this particular tree is satisfying Hoffman tree? If this tree is satisfying, okay, someone has a doubt related to NYT, and Uday is also saying that we have to uh, repeat again as he is not understanding. No doubt. I'm starting from the beginning. Like, what is the purpose of NYT? NYT's purpose is simple. Whenever we have a new character that is not transmitted earlier, we will be using NYT as a left node. Each and every time, whenever a new character, that character will be on the right side. Left side will be on the NYT. So here in this particular algorithm, if you are checking, this is A is the character, it is on the right side. A is the character, it is on the right side. If we have a R is introducing for the first time, we are adding this R to the right side. If we have a D for the first time, we are introducing this D on the right side. If we have a V is also introducing on the first time, we are adding this V on the right side. So the simple rule is we have to use NYT on the left side when we have a new character in the tree. If we like from any point, like if we have at this step another string is another D, R or A. I'm saying again, if we have A is repeated, R is also there, D is also there. If we have a new A after A, R and D, then if new A is there, we will increase the weight from 2 to 3. If we have a new R, we will be increasing a weight of R from 1 to 2. Or we will have a new D, then we will be adding this here. But if we have a new character like V, so we have to add that character on the right side of the tree, and NYT will always be on the left side. So in the whole tree, we will have only one NYT, and that NYT will be on the left side. First thing. Weight of the NYT is always 0. Weight of the NYT is always 0. When NYT is introduced, whenever a new term is there, we are introducing NYT. Like again, after AARD, so here AARD is completed, we have a new character V. When V is completed, we have a tree like this. And from each step, after each step, we are checking the Hoffman property that from left to right, is it in ascending order or not? If it is not in ascending order, then we are swapping the nodes. So I'm starting from the first step. If you have any doubt, please raise your questions. Someone is saying repeat the third part. Okay, I'm repeating the whole part. No issues. So initially there are no characters in the string. Initially we have only NYT. That is okay. At step 1, we have this A. When a new character is coming and that character is not introduced yet, so we are placing that character to the right of NYT. Is there any issue? No issue. Okay, fine. So we are adding the total of these two. NYT has always value 0, and the new character is repeated one time, so it has a weight 1. This 0 and 1 is not the weight. Weight means inside the box what we have, that is the weight. 0 and 1 is representing 0 for the left side, 1 for the right side. So do not confuse ever. Why we are using these 0 and 1, I will tell you later when we are using these swapping modes. Okay, so we have a total of 0 and 1 is 1. I think there is no issue with step 1, and I'm using that chat to everyone, so everyone can write at one place and I can easily check that. So you are allowed to write on everyone. So first step is clear. Second step, we have another character. That character is already introduced in our last step. That was A. So here A has a new like A is already transmitted character. So here we had a weight 1. We are updating the weight 2 as new character is also A. So 0 and 1, after adding, we are checking Hoffman property from left to right. Is it in ascending order 0 and 2? Yes, it is in ascending order. So we are adding 0 and 1, like 0 and 1 means these are the left and right node. We are adding, the total is increased from 1 to 2. Any doubt in first two steps? Please let me know. I'm moving for the third step. Third step means we have a new character. New character means new character is R. So this much tree is already there. One, sorry, NYT was there 0, and here was the 2. But here what we are doing, we are adding a new character R. So we are switching the NYT to the bottom and making it blank. Blank means without any use. So this will be the internal node, as external node is always on the brackets, rectangle. So NYT is on the left side and we have a new digit R. R is on the right side and R has a weight 1. NYT is always has weight 0. This is the left node, this is the right node. After adding this, we are checking 0 plus 1 is 1. We are checking 0 plus 1 is 1. Then thereafter, we are checking the Hoffman property. Is it satisfying? The Hoffman property means left to right is in ascending order. Here we are checking weight 0, weight 1. These are ascending order, no issue. Yeah, here we are checking here, like we have weight 1, weight 2 in ascending order, we are fine. Here we have a weight 3, we all set. So no swapping is needed for this. First three steps are clear. If you have any doubt, please raise your question. Otherwise, I am moving for the step 4. Another digit is coming, that is D. So in the same way, we were introducing R, we are introducing D. How we are introducing? We are shifting this NYT to the bottom and D is there. We are adding the D to the tree as an external node. We are checking the total 0 and 1. We are showing 1. Then this R was there. R has a weight 1 and now he has that NYT and D has weight 1. We are updating the weight 2 in the internal node, and then thereafter if this is 2 and this is 2, we will be updating this weight 2 and 2 is 4 at the root. This step is similar step as we were using for R and initially for A. If you have any doubt, please raise your question. After adding, we are checking the Hoffman property. From left to right, it is in ascending order at each level. Level means here also, here also, here also, here also. So we are checking from the bottom 0 and 1 in the ascending order. Yes. We have 1 and 1 in ascending order. Yes. The rule is either we have the same value left and right, or we have a higher value on the right side. Here we have 2 and 2. We are satisfying Hoffman property, and here we have 4. We have no other term to uh, compare. So this tree is also satisfying Hoffman property. Now we are moving another step. What will be the next digit? Next digit will be V. We are introducing V. So in the same way we were using D, like till now there were no issue. Here we are shifting NYT to the bottom and we are adding R V. So 0 and 1 is 1. Here we have D. So instead of this 0, we have 1 at this place. So 1 and 1 is 2, and 2 and 1 is 3, and 3 and 2 is 5. So after adding all, we are checking Hoffman property. Is that particular tree is satisfying Hoffman property? Can you please check that from left to right, this tree is satisfying or not? We are on step 5. Here is the step. Can you check? Yes. This, like, we are starting from the bottom. We have this particular, we have 0 and 1. So this particular thing is not satisfying. Like 0 is on the left, 1 is on the right. Adding that, we have 1 at this level. We have 1 and 1. This step is also satisfying. No issue with that. We are moving at this level. We have the total of 1 and 1 is 2, which is on the left side, and R is on the right side. So this step has a issue, and then we have this step also has a issue, as 3 is on the left and A is on the right. So what we have to do, from where we have a issue, like this node was 1, as it was on the right side, and this node was 0 on the left side. So we have always right node has value 1. So we are shifting this A to the left and this entire leg to the right. When we are shifting the entire leg to the right, it means all the children node are also shifting with that. So A is shifted there and we have 3. So at this level, we have no issue with the Hoffman property, as 3 is after 2. And at this level, we had an issue. So we are shifting R, this R to the left side and this whole leg to the right side. We are swapping these. And at lower level, we had no issue from this to this. So this whole leg is shifted to the right side and without changing anything. If anyone has issue on step 6, that was swapping of nodes, please raise your question. Swapping is easy, but just you have to understand the where is the difference. We are starting from the upper side, where we find like 3 is before 2, so we are shifting this entire leg to the right side, and this A is to the left side. When we have this also, then we are shifting this entire leg to the right side, and the remaining is on the left side. That's fine. So another student is requesting for one more time to repeat. So here, like from the upper side, we are finding problem here first. Then thereafter at this level, we are shifting the lower to the left and upper to the right. So we are swapping the legs. Like A is on the left side and the entire tree and its sub tree is on the right side. We are swapping at this level, and here at this level we have also problem with 2 is on the left side and R has a weight 1. So we are shifting R to the left side and entire second leg is on the right side. Is it okay? I think swapping is easy. You just need to find the level. At what level has a issue? We are shifting the level. Then again, what we have, we already done with V. So the remaining is A, R, and K. You can check that A and R is already covered. So we are just updating the weight of A as well as R. So like next is A. We are using this tab for A and this tab for R and this tab for K. So how? Where is A? A had initially weight 2. Now we are updating the weight of A is 3. And we after updating the weight, we are checking is there any issue? Is swapping is required? Is uh, Hoffman property satisfied? So that was 2, this is 3. So 3 and 3 are there is no issue. If we have the same weight, we can use that weight as it is. No swapping is required. If A had weight 4, then we had to swap. Is there any issue with this type? I think there is no issue. Then we are checking for R. Where is R? R is here is R. So R initially had weight 1. Now we are updating the weight of R is 2. And again we are checking Hoffman property. If it is satisfying, then there is no issue. I think 2 and 2, it is satisfying. There is no issue. Then we are moving forward to K. K is what? We have K is the new term that is not introduced yet. So we have to update at the bottom. So where we are using NYT is here. So we are shifting this NYT to the bottom and updating the K, and NYT and K has a total 1. 1 and 1, it is satisfying. We have uh, this is 2, this is 1. So what we have to do? Here we have a total 2, here we have a total 1. So in our next step, what we are going to do, we are shifting this D to the left side and this entire leg to the right side. And uh, lower part will be as it is. So moral of the story, this could have a way like this could be 1 and this could be 0, as it will be on the left side, and the entire bottom tree will be on the right side. So we are cover up with all the symbols. If I ask you uh, to drop the value of A equals to, then R equals to, then D equals to, can you add the total value for A and R, A, R, D, V, and K. These are the total different characters we have. You can give me the like code for all these. Can you tell me? For A, what will be the byte code or compression code? Like A is at the starting. A has a value representing 0. So A could have a value that is representing 0. And another term is R. So what will be the code for R? R is where? R is there. So the path for R is 1 and 0. So we are representing 1 and 0 for R. And for next is D. Where is D? D is there. But D will be on the left side. So D will have a weight, not weight, has a value 0. So 1, 1, 0 will be used for D. And what will be used for V? Can you guess? 1, 1, 1, 1 will be used for V. If someone has a problem, then please let me know. And for K, what will be the number? 1, 1, 1, 0, and 1. 1, 1, 1, 0, 1. 1, 1, 1, 0, 1. If someone has a doubt, please raise your. Rahul was writing like 1100. I think uh, that was changed because from here we have to update the tree. 2 will be on the right side. The issue was there. The enough space was not there to show the last step. So that step is covered without showing it. Any issue? Please raise your question. Yes, Jishan has a raise hand. Okay, Jishan is asking to repeat again. From what step I have to repeat? Because we already on the repeat mode. After completing one time, we are repeating this for the second time. Till now, where you are understanding and from where I have to repeat. That is the question. Last step. That is fine. So how we are calculating ARDVK? Like A had a frequency, like most frequency is used by A. A had repeated 3 times. So we already used it in the Hoffman tree that if higher the frequency, lower the code. So here, higher the frequency means if we have A repeated on the 3 times, then A had a frequency like A had a value 0 as a code or the transmission code. And for R, we have R is repeated for 2 times. So R is again the value 1, 0. Other than that, all have value frequency 1. So all have value 1, 1, 0, 1, 1, 1, 0. And for V and K, I will explain again how this is 1, 1, 1, 0 and 1, 1, 1, 0, 1. Where is V? V is here. So we had a value starting from the root node. We have a 1, 1, 1, and 1. Okay. मैंने mistake किया. So we had a value 1, 1, 1, 1. Yes, that was absolutely correct. That we had a value 1, 1, 1, 1. Absolutely correct for V. And for K, is it correct? 1, 1, 1, 0, 1. Like K is correct. And we had a value 1, 1, 1. My mistake. Any doubt? Manoj is asking how to decide internal node. Internal node is nothing but every time whenever we have a node, after that node, if we are shifting, like we have to introduce a new node, then NYT is shifted to the bottom, and beyond the NIT, we have a right side, we are using the new term. Like after deleting all the drawings, I am showing again. Like initially NYT was there. Like here is the NYT. We have a new term A. We are shifting NYT. We are adding this A. Here is the total. When we are adding the total, this is the internal node. This is the internal node. Here we have a new A. A is already transmitted. So no change in NYT. We are just updating the A. Internal node value is updated. We have a new value R. So we are shifting this NYT to here. We are adding the R and making this to the internal. That is the logic. Whenever we have a new term D, so what we are doing, we are shifting this. Here we have an internal node. D will be like in rectangle, and a new one is also at the leaf. Whenever a new digit is there, it will always be on the leaf node and to the right of NYT. Like the left side is always represented by. I hope it is clear to all of you. Then moving forward. So arithmetic coding with higher order modeling. Why we are using context modeling, and before encoding begins, I have to delete these annotations, drawing, and so arithmetic coding. Next coding is arithmetic coding with higher order modeling is an advanced technique used in data compression. So traditional arithmetic coding operate on a single symbol at a time, assigning a unique code to each symbol based on its probability of occurrence. So, however, in the higher order modeling, the encoding process takes into account only not only the current symbol but also preceding symbol or context to better capture the statistical dependencies present in the data. So I'm going to give you a brief about arithmetic coding with a video. So I'm playing the video. Try to understand that.
And
then we will start the.
In order to overcome this drawback, we are going for arithmetic coding. Arithmetic coding is a string-based encoding, that is, a source symbols is encoded as a string of code symbols. This technique is used in lossless data compressions. This code is a non-block code, which means the arithmetic code does not generate individual codes for each character, but performs arithmetic operations on a block of data based on the probability of this next character. It works very well for sequence with low entropy. Now we are going for arithmetic encoding procedure. Let's start with the examples. Consider the transmissions of a message when dot comprising a string of character with the probability E, 0.3, N, 0.3, T, 0.2, W, 0.1, dot 0.1. Let's start with the procedure. Step 1. Divide the numeric range 0 to 1 into number of different symbols present in the message. Step 2. Expand the first letter to be coded along with the range. Further subdivide this range into number of symbols. Step 3. Repeat the procedure until termination character is encoded. Now we will enter into this problem. Step 1. As I told, the range 0 to 1 is divided into 5 different symbols because 5 symbols is given in this examples. That's why the range is taken between 0 to 1. This range is divided into 5. Now allot the interval based on that probabilities. Look at that problem. The first symbol is E and the probability is 0.3. So 0 to 0.3 interval is E. And next probability is nothing but 0.3 and respective symbol is N. So 0.3 plus 0.3, 0.6. The next range is 0.3 to 0.6 is N. And next letter is T and the probability is 0.2. So the range is 0.6 to 0.8. Next symbol is W. The range is 0.8 to 0.9. The last range is 0.9 to 0.1. The respective symbol is dot.
Like these are the probabilities given. You always understand that what exactly a probability is. Probability is the occurrence or the chances of occurrence. Like if you have a dice, what will be the probability of any of the digits from 1 to 6? Probability will be 1 by 6. If you are tossing a coin, then what will be the probability? Probability is 1 by 2 or 0.05, like 0.5. 0.5 means either that coin will have a head or a tail. Is it fine? So probability is always lying between 0 and 1, whatever the number of chances it has. If it is a dice, we have 1 by 6. So it is lying between 0 and 1. If we have a like coin, we have a probability lying between 0 and 1. So probability of tossing a coin is and it is head or tail, the probability is 0.5. If I have 10 balls or 5 balls, and how many of these are like I'm juggling it, and how many times if I'm finding a ball out of these, there will be a certain probability, like what colors ball will be there. So that probability is always lying between 0 and 1. Any of the cases there around the globe, we always start with 0 and ending with 1 in term of probability. If there are 100% probability, it will be 1. If there are 0% probability, it will be 0. If we have 50% probability, it means 0.5. So here we already have introduced the question. Each probability is given, like for E, we have a probability 0.3. For N, we have a probability 0.3. For T, we have a probability 0.2. For W, we have a probability 0.1. And for this dot symbol, we have a probability 0.1. The total of these probability is 1. Because 0.3, 0.3, 0.2, 0.1, 0.1. If you are adding these, then there will be a value 1.0. That means total of all these is 1. So what we are showing here at this level, we are showing E has a probability 0.3. So 0.3 means we have a value starting from 0 to 0.3. N has a probability 0.3. So we are starting from 0.3 to 0.6. Total will be 0.3. Here we have T has a probability 0.2. Starting from 0.6, we have 0.8. That will be total 0.2. And for W, we have a probability 0.1. Then from 8 to 9, we have 0.1. And for this dot, we have a probability from 0.9 to 1. I think there is no issue till now. Then moving forward.
Step 2. Expand the letter to be coded. Look at the message when dot. The first letter is W. That W letter is going to be coded. The W range is nothing but 0.8 to 0.9. Now we need to expand the range 0.8 to 0.9 with the symbols W. Again,
what was the problem? We had to provide W, E, and T and dot. This was the problem we had to solve. I'm writing in the chat. We are going with W, then E, then N, then T, then dot. We are starting with W.
8 and 0.9 is taken here. That range is divided into 5 different symbols based on that probability. Now we need to find out the range. The range is calculated by using this formula. Before going to this formula, we will know the difference of this range. So the range is the difference is calculated by upper bound minus lower bound. Here upper bound is 0.9 and lower bound is 0.8. 0.9 minus 0.8 is 0.1. So after that we will calculate the range of the symbols. The range of the symbols formula is lower limit colon lower limit plus D probability of the symbols. Now we need to calculate the range of E. So formula already known. Now we substitute the values in this formula. We will find the range. First one is range of E, and lower limit is 0.8 colon lower limit is 0.8 and D is nothing but 0.1, that is the difference, and probability of the symbols, probability of E is 0.3. So substitute this values. After calculating we get the range is 0.8 to 0.8.
So we are running over time. I'm sharing the link of this video with you, and we will start our next session from the same video. You can, if you have time, then you can go through with the video and try to understand the encoding procedure given in that video. This is a 16-minute video. First 11 minutes is showing the encoding technique. Then after 4-5 minutes, there is a decoding method. Whatever we are encoding from a digit, string of characters to the code, and then from code to the string. So this is one of the good videos where you can easily understand the procedure, and we will discuss after after playing this another 5-7 minutes video. We will have step 1 to step 4 or 5. First we are calculating for W, then we will calculate for E, then we are going to calculate for N, then T, and then dot. When we have a dot, then we will have a lower and upper limit. Those lower and upper limit will be the answer for our solution. So if you have time, then please watch this video. And if you have any issue related to adaptive Huffman coding, you can also watch a couple of videos if you are not understanding, or watch this particular recording of this particular lecture. And if you have any doubt, then we can have another discussion on this. Next might be the last lecture. So we will try to cover another couple of coding methods. Coding methods will be the main part of your multimedia subject. And apart from that, we will also in multimedia. So I think utilize the best time you have and try to make it full. So thank you guys for today's session. As we are running behind, if you have any questions, please raise your questions next time before going to start. then we are going to start from this same video, and we will move forward for another techniques. I'm checking if anyone has an issue. Like till now we have completed. We are going to be in our exams perspective. So don't worry about the exam. Uh, we have completed first like 3 or 3.5 units already. So you have to prepare all these 3 units. So thank you guys.